Hi dear students, hope you are all fine, doing well and staying at home. Now today in this video we will talk about the differentiability of uh, chain rule of differentiation in the space Rn, chain rule. Before discussing that, I will recall you the definition of differentiability of functions in Rn. We say a function f from some subset S of Rn to Rm is differentiable at an interior point of S, interior point A of S, interior point A of S, if there exists a linear map TA. Actually this TA is the total derivative of f at A, and it's actually TA is actually f dash A, total derivative of f at A. Linear map TA from Rn to Rm such that the first order Taylor's formula holds, that is f of A plus y is equal to f of A plus, you can write TA or f dash A, f dash A of y plus norm y into AY, where AY tends to 0 as y tends to 0. You know, this is a definition of differentiability of functions, or you can say differentiability of vector fields. It is exactly the analog of differentiation in one-dimensional case when you have functions from R to R. So we call this as the first order. It's exactly the way we expand, or we construct the Taylor expansion of a function. You know, there you have f of A plus h is f A plus h f dash A plus h square by 2 factorial f double dash A, and so on. So here you have f of A plus y is f of A plus f dash AY plus norm y. In fact, this is the first order Taylor's expansion. So we say a function is differentiable if this holds, where this is the remainder after these terms. Norm, this AY tends to 0 as y tends to 0. Now assume the function f is differentiable, then this will hold. This will hold. As y tends to 0, this will tend to 0. Now if I let y tend to 0 in this formula, I get f of A plus y, limit of f of A plus y equal to f of A plus, since y goes 0, so here you will have 0, because actually the linear transformation is always a continuous map. So you can simply here say, since y tends to 0, so this factor will go to 0, this term will go to 0, and this will tend to 0 by definition of differentiability. So you can say here limit y tends to 0. I assume this holds, means I assume the function is differentiable. So limit y tends to 0, f of A plus y is equal to f of A. So I can say this implies that it is continuous. Vector field is continuous. This is quite obvious. This follows trivially from the definition. So if a function is differentiable, if you have a differentiable vector field, that is trivially continuous. Means you can write limit y tends to 0, f of A plus y is equal to f of A. Now let's come to our main topic, the chain rule. Chain rule says if you have two functions, chain rule in Rn. This is if G from Rn to Rm, so it's a vector field here, is differentiable at A with total derivative at A G dash A. It's a differentiable vector field at a point A, and its total derivative is G dash A. In fact, in the last videos we used TA. Since you have so many functions here, so I will use this notation. Actually, G dash A means the total derivative of G at the point A. So this is the first function, and f from Rm to some other space, say Rp, where n, m and p are positive integers, is differentiable at, so this f is differentiable at the image of G under the point, image of A under the function G, image of A under the function G. So it is differentiable at, say, point B, where B is equal to G of A. Then f is differentiable at A, f is differentiable at B, where B is G of A, with total derivative f dash of B at B. It is differentiable at B. The total derivative at B is f dash of B. Then what we have to prove? Then the composition map. How can I construct that? I have G from Rn to Rm and f from Rm to Rp. F operation G is differentiable. I have to show it is differentiable at A and the total derivative of this composition map at the point A is equal to f dash of B operation G dash of A. We have to see this holds under the given condition. G is differentiable at A with total derivative G dash A, and f is differentiable at B, where B is actually the image of A under the function G, and the total derivative of f is given to be f dash of B. We have to show the composition map is also differentiable at point A, and f operation G dash at A is equal to f dash B operation G dash A. Here you cannot write the ordinary multiplication because you do not have these as real functions. In the ordinary calculus, where you have the one-dimensional space, there you write, if you have, suppose, differentiation of sine of cos of x, sine in the angle cos x, you say it is simply cos of x into minus sine of x, internal differentiation. That time you simply write into, because you have the one dimensional where the multiplication is simple, multiplication of numbers, but here you have the composition. This is not a number here, you cannot write this number multiplied with this number, so there must be operation inside. Now I have given G from Rn to Rm and Rn to Rm and F from M to Rp. So the situation is like this. You suppose this is your Rn and this is Rm, this is Rp. You have G between these two and F between these two. So G is given to be differentiable at point A. The image of A will be G of A here. Now F is given to be differentiable at GA, which is actually B. F is function from M to Rp. Let me denote the composition by, let H is the composition of F and G. Then clearly, when H is a map from Rn to Rp, this is the domain and codomain for the function H. Now, I have to show this H is a differentiable function. Of course, it's also this vector field because the range is again in Rp. So, I have to show now this H is a differentiable vector field. So, I must show that very first order Taylor expansion holds. We have to show H of A plus some vector say Y is equal to H of A plus. So I will write the derivative of H here because I have now three functions here. One is F, second is G, and third is H. So I can write here H dash of A of Y plus norm of Y into E, say A Y, where I have to show E A Y tends to 0 as Y tends to 0. So I have to establish this relation with this condition, holding for this relation. This I have to establish. I have to use the fact that F and G are differentiable functions at the given points. Now let us calculate this difference, H of A plus Y minus H of A. So what is H of A plus Y minus H of A? This will be, the definition of H is given to be F operation G. So it is F operation G at the point A plus Y minus F operation G at the point A. Now you know the definition of composition of functions. Its value will be here F of G of A plus Y minus F of G of A by definition of composition. Now this term I can write as F of G of A plus G of A plus Y minus G of A, then minus F of G of A. Sorry, this is equal to F of, I will give some name to this difference. This is B because this is given to B. This is B plus say V minus F of B. So I have H of A plus Y minus h of a equal to this. Let me call this as 1. Where v is equal to g of a plus y minus g of a, the value of this one. So v is this thing. Actually, I want to put this difference, which is actually this, that is this one. So I want to put this difference equal to h dash of a something here. That must be a linear map with this y plus norm of y plus some error here which goes to 0 as y goes to 0. Now we are given that this function g is differentiable at point A. G is differentiable at A. So I can say v, which is actually g of a plus y minus g of a. G is given to be differentiable. So there is a first order Taylor formula for this function g. So I can write this as actually g of a plus y is equal to g of a plus g dash of a into y plus norm y times some error there. So this difference will be equal to g dash of a y plus norm y times corresponding error. So I can write a y, but I have 3 different functions. So I will use subscript here. This is for the function g, where you can write before this, since g is differentiable at a, therefore we must have this one, where the error e g at ay tends to 0 as y tends to 0. I am simply using the definition of differentiability of function g. Let me call this as second. Now I have h of a plus y minus h of a equal to f of b plus v minus f of b. And I know f is given to be differentiable at b. So this error, this difference also has this type of expression. Again, f is differentiable. F is differentiable at point B. Therefore, I can write f of b plus v minus f of b equal to, this will be f dash of b, exactly the derivative of this. Usually we were denoting these types of derivatives, g dash a, f dash b, t a, t b. Now here I am using the exact names, g dash a, g dash b. t a we are giving actually the name because it's actually a linear map, so we are giving the corresponding symbol for this derivative, otherwise this is a derivative. So it's y here, I'm sorry, this is v here, because this time I have the vector v. So it's v plus norm of v into e bv. But now I have the function f, so I can write f here. Now you can see here, I am using v here. You should understand first of all, v is a point of Rn. Now what's actually v? V is the difference. G of a plus y minus g of a. You know, g is a function from Rn to Rm. Rn to Rm, and you know a and y are the points of Rn. So their sum is also there. Applying g is a point of Rm. This one. This is also a point of Rm, and Rm is a vector space. Difference is also there. That means v is a point of Rm. So I can apply. I have the function f from Rm to Rp. So this is a point of Rm. So I can use the definition of differentiability. Now in this f value, I will use the value of v. So using second, we get f of b plus v minus f of b is equal to f dash of b. Value of v is g dash a y plus norm y e g a y. In this one I forgot to write, actually when this f is given to be differentiable at b, so this difference will be equal to this plus this, where ef at, should mention this, tends to 0 as v tends to 0. This is understood because g is given to be a differentiable, sorry, f is given to be a differentiable function at the point b. Now I am substituting the value of v from second, so I get f dash b times this value, then plus norm of v, e f and b v. Now I will use the linear property of this f dash. F dash b, actually our f is from Rm to Rp. Therefore, corresponding derivative at b, which actually is t of b, that is a linear map from Rm to Rp. As we know, when we construct the derivative of differentiable vector field, that's actually linear map. So f dash b is a linear map. I can use the linear property of f dash b here. So I can apply, when f dash is a linear map, I can say alpha of some x plus beta of y. If I have suppose x and y here, I can write alpha of f dash of b at x plus beta f dash b at y, when x and y's are the elements of Rn. Now I can operate this. First of all, I have to understand whether these are the elements of Rm or not. See, y is the element of Rn. Y is from Rn, and g is actually a function from Rn to Rm. Its corresponding derivative g dash a is from Rn to Rm. It's a linear map. So when we evaluate this g dash a at any point of this one, that will belong to R of m. So g dash a of y will belong to Rm. So this is a m vector, because this is a linear map. Its corresponding matrix also as m cross n. When we evaluate at any point of Rn, so that belongs to R of m. Again, this is a real number here. You are applying norm. Norm is a function from Rn to R. So this is a real number. You can take it out like you are taking alpha here out. And this one, this EGAY, this is also the element of Rm. How is this element of Rm? You can see corresponding definition. That's here. See here. Forget about this first of all. This is the point of Rm. This is the point of Rm. This is the point of Rm. Transfer this to left side, then divide with this. So it's actually EGAY is a scalar multiple of GA plus y minus GA minus G dash AY. And these are the elements of Rm. Rm is a vector space. Scalar multiple of this is a vector in Rm. So this is the element of Rm. So I can say this is the element of Rm. So I can operate this. It's like now alpha, this vector here, alpha times, so it's x plus alpha times y. This is a linear map. So I can evaluate this. It will become here. But once I operate, f dash is linear map, g dash is linear map. I cannot put the ordinary multiplication in between, because this is here a linear map. So I can write this as f dash of b operation g dash of a, and this one operated at y, plus norm of y, this is scalar, alpha will come out, this will go to this one, because this is m vector here. F dash of b into e GAY plus norm of V into EF BV. B times V. Now this is the value of f of B plus V minus f of B. If you go in equation 1, there you have actually h of a plus y minus h of a equal to this thing. I will substitute. Use this value. Use this value. Use this difference. This difference in 1 we get. Using this difference in 1 we get, what's 1? 1 is actually h of a plus y minus h of a is equal to. This is equal to now f dash of b operation g dash of a into y plus these two. In these two, I will write norm of y times, I will take norm y because these are real numbers. This will be f dash of b e.g. ay e.g. ay plus EF B comma V. So I can say h of a plus y minus h of a or is equal to h of a plus f dash of b operation g dash of a y plus norm of y into EAY, where EAY is equal to f dash of b EG AY plus, sorry, here I will have norm of v. That is also norm of v. So it will be norm of v by norm of y into that very E f of b comma v, because you are taking norm y out. So EAY is f dash b EGAY plus norm v by norm y into EF of b comma v. So I have a type of Taylor formula for h of e plus y is equal to h of e plus this quantity times y plus norm of y plus this. If I can show this error tends to 0 as y tends to 0, I have this EAY equal to this quantity. Now if I can show this error goes to 0 as y goes to 0, I will have the differentiability. But there's one question, the function f is said to be, or h is said to be differentiable if ha plus y is ha plus some linear map here into y plus norm y into EAY, where this goes to 0 as y goes to 0. So we have to confirm whether this is a linear map or not. You might have studied in elementary classes or at elementary level or in lower classes that composition of linear maps is always a linear map. You are already given that f dash is a linear map, f dash b is a linear map, g dash b is a linear map. You are composing the two, or yes, you are composing these two, and actually f dash is from R of n to R of n, and you have g actually from R. This is G is actually map. G is from Rn to Rm. So corresponding G dash is a mapping from linear map is from Rn to Rn between the same spaces, and similarly f is from Rm to Rp, so f dash of b is from Rm to Rp. So I can compose the two. Rp, I can use the composition here. G dash A compose f dash of B composition G dash of A. That is this thing. Composition of two linear transformations is always a linear transformation. So it remains only to complete the proof. It remains only to prove that this tends to 0 as y goes to 0. In fact, one term is trivially tending to 0 because you know G is a differentiable map. G is a differentiable function. You know, e.g. a y tends to 0 as y tends to 0 means this will tend to 0 as y tends to 0 because this is here, this is independent of y, so this vector, this is here. In fact, you can say this is a matrix times 0 here, 0 column, when you operate that will be 0. And you know, e, f, b, comma v. Now what about this v? Does this tend to 0? What about b is v? You know, v is this thing, g of a plus y minus g of a. You can call this, okay, v is this one. Now if y tends to 0, focus on this one. If y tends to 0, you know, G is a continuous map because every differentiable function is continuous, as we have seen before. This one in the introduction, every differentiable function is continuous. As y tends to 0, you know, limit y tends to 0, g of a plus y is equal to g of a because g is continuous at a. It is differentiable actually at a, so it is continuous at a. So when I let y tend to 0 in this quantity, I get ga here. Ga minus ga is 0, so v will tend to 0. That means if y tends to 0, if you let y tends to 0, that will imply v tends to 0. So this v tends to 0. But you know, as v tends to 0, e, f, b, comma v tends to 0 by the differentiability of f. So y tends to 0 will imply this quantity tends to 0, this quantity tends to 0. But the question remains of this one. This one. What will happen to this? Because we have y in the denominator. For this I will use that very boundedness of a linear operator which we have seen. So it means to see the behavior of this as y tends to 0 because we know now as y tends to 0, this tends to 0 and this tends to 0 because as y tends to 0, g of a plus v is g of a, that means v will tend to 0. And by definition of differentiability of f, this tends to 0. Now let us see the behavior of this ratio as y tends to 0. This we have to discuss because y is here in the denominator. From second, we can see from second that v is equal to this. We get norm of v is equal to, I can use triangle inequality, norm of v will be norm of this quantity, and this norm is same as we have discussed the norm in Rn. We have the same space here, so this should be less than or equal to norm of g dash a y plus norm of y inside norm of y into eg a y of norm. Now we have seen in the previous video that Ta of y, that was actually for this very result, that very boundedness of a total derivative. In that video we have seen Tai, norm of Tai is actually less than or equal to m fa norm y, where you know this m fa is actually summation k run from 1 to m delta k of fa, delta k of fa. This is that quantity. This is a real number, this MFA. This is actually the total derivative of the function f. Now in this case you have g, function g. So g dash a is the total derivative of g. And you know this is linear because TA is linear. When TA is linear we use this inequality. And total derivative of a vector field is always a linear map. So I can exactly use this inequality for function g. So I can say this is less than or equal to m g a norm y plus. This is the inequality of bounded linear map. G dash is a bounded linear map. I have used the corresponding inequality which I have obtained for the bounded linear map, inequality for the bounded linear map in the last video. Now here this is C because this is a positive real number, or you can say a non-negative real number. Norm of constant times the vector is mod of the constant, but the constant here is positive or non-negative because you have already applied norm on y, so it will come out to be norm y into norm of Eg ay. Norm of this. Now from this inequality I get here norm Vy, norm y. I will divide by norm y. But I cannot divide actually by norm y because I have to see first of all whether y is 0 or not. If y is 0, then the corresponding equation will hold trivially. If y is 0, then you have h of a, this is 0, this is 0. So in that case you have nothing to prove. So it's understood we have to discuss only for non-zero y's, because when y is 0, this is already 0. So this should be less or equal to mga plus eg ay, norm of this number. Now you can see here this tends to 0 as y tends to 0 because of the differentiability of g. There we see eg ay tends to 0 as y. You can see the definition of differentiability of g. Now this is a positive number, or non-negative you can say, at least. Generally this is some number independent of y. It's constant. So I can say when y goes to 0, the limit of this quantity will remain less than or equal to this. So I can say this quantity is bounded because this tends to 0 as y tends to 0. Since you can say eg ay tends to 0 as y tends to 0, therefore norm v by norm of y is bounded as y tends to 0. As y tends to 0. So when y tends to 0, this ratio remains bounded. That means when I apply limit y tends to 0 here in EAY, I have already confirmed that this tends to 0, this also tends to 0. This is a finite number. So the overall limit will go to 0. I think you have understood this, that EAY is a dash of B EGAY plus this quantity. Now this tends to 0, this tends to 0, and I have confirmed now that this remains bounded as y tends to 0. So I can simply say that EAY tends to 0 as y tends to 0. Thus, EAY, which is actually, what was that? EAY, which was perhaps EGAY plus, just before this was here, plus that very norm of y, v over norm of y into E f at b comma v tends to 0 as y tends to 0. Thus, or you can say, therefore h of the function h of a plus y is equal to h of a plus what was that, f dash of b operation g dash of a y plus norm y into e a y, where we have seen e a y tends to 0 as y tends to 0, implies h is differentiable because we have first order Taylor formula for y. H is differentiable at a. And you know, when you have the definition of, you have the Taylor formula of function, you have Taylor formula here, then this is the total derivative of h. And what is the total derivative? Total derivative is h dash a, but h, you know, h is actually f operation g. So f operation g at a, value of h, that is f operation g at a, is equal to, you have seen this ha plus y is ha plus actually the total derivative of h. But that I have this thing, so I can say this is equal to f dash of b operation g dash of a. You can see this is actually f dash, what is b? That is g of a operation g dash a. It's like you are differentiating this, or you can say, or here f, when you compose this, this is the f of g of a dash, derivative of this. That is simply the derivative of this internal differentiation type of equation, f dash of g into g of x. In the general, in the one dimensional case, you say into there multiplied, but here you have the composition because these are the operators. These are the operators, so you have a corresponding composition. Or you can say, in this case, this would be a matrix multiplication. In between these two, you have the matrix multiplication as the operation. Okay, this was the chain rule. I hope you have understood everything. Was a bit lengthy, but not difficult. Thank you.